Last time we were looking at limits from a graph, and we were taking a look at one-sided limits. Today we are going to be evaluating limits algebraically. So to begin, we are going to look at some properties of limits. Oftentimes we have a sum of two different functions, and the limit of a sum is the sum of the limits. And in my written notes, I have that written down. The limit of a sum is the sum of the limits. So it appears that we're distributing that limit through the parentheses. That's what it appears to do. So the limit of a sum is the sum of the limits. Similarly, the limit of a difference is the difference of the limits. It looks like the limit is being distributed. If you want to think of it that way, you can, but I'd rather you not. I would just like you to know that the limit of a difference is the difference of a limit. The limit of a difference is the difference of the two limits. If you have a product, the limit of a product is the product of the limits. That's why I didn't want you to think about it distributing, because we don't distribute things like that. If you have a product, you don't distribute the outer number to both pieces. If you have 2 times 3 times 4, that is not 2 times 3 times 2 times 4, right? So you don't distribute like that. So the limit of a product is the product of the limits. Similarly, the limit of a quotient is the quotient of the limits, assuming that the limit as x approaches a of that denominator function is not 0. And the last little property that we have is if you have a constant being multiplied by a function, you can take that constant outside of the limit. So it can be multiplied by the limit of the function. You can only do that if if it's a constant, a number. If it has x's in it, you cannot do it. And you can only do it if it's being multiplied by your function. If it's being added, you cannot take it out. It has to stay. Okay? All right. We have several methods for evaluating. What did I do here? Okay, there you go. All right. We have several methods for evaluating limits algebraically. All right. And the first method is substitution. And it is definitely our go-to. We always do this first. Just plug in the value of x that we are approaching. This isn't written right. That sounds kind of funny. You're going to take this number and you're going to plug it in for the x. Okay? See if you get a real number. What is a real number? It's not undefined. It's not infinity. Okay? So, plug in that value for x. See if you get a number. So here, if I plug in that number for x, I get 4 minus 8 divided by 2 minus 4. So I get 2. Is 2 a real number? It sure is. So my limit is 2. Easy peasy. Okay? Start by plugging in 2 for x. If I plug in 2 for x, in the numerator I'm going to get a 6. In the denominator I'm going to get a 16. That reduces to 3 over 8. So I could say that that limit is 3 over 8. Okay? Plug in 0 for x. The numerator, sometimes I do it like this. The numerator is going to, if we put 0 in for x, the numerator is going to 5. The denominator is going to negative 3. So this limit is going to, or this limit is equal to 5 over negative 3, which as a multiple choice answer would be negative 5/3. Okay? Alrighty. plug in 0 for x. If we plug in 0 for x, cosine of 0 is 1. If we plug in 0 for x in the bottom, we get 0 in the bottom. What's happening there? Can we divide by 0? We cannot divide by 0. This does not exist. Okay? And we'll talk more about that in a moment, but that is it does not exist. I will say this though. We have 1 divided by a teensy number. 1 divided by a tiny number. So if you got out your calculator and you took 1 and divided by 0.0000001, you would get a huge number, right? You get a huge number. So this is going to infinity. But what if this teensy number close to 0 was negative? Then you would be going to negative infinity. So both of those, regardless of what it is, both of those are does not exist. This would be a does not exist. Okay? Notice that I did not put an equal to sign here, and you should not put an equal to sign here. You cannot, your limit cannot equal a non-existent number, okay? A non-existent thing. So don't put an equal to sign here. All right, sine of 0. Sine of 0 is 0. 7 doesn't have an x with it at all. So we have 0 over 7. What is 0 divided by 7? Well, 0 divided by 7 is just 0. So this time we could put equal to, because this is just 0. Let's let x go to infinity. As x goes to infinity, what is happening to e to the x? If we let x go to infinity, what is happening to e to the x? This is going to infinity very quickly. That's going to infinity. Natural log of 2 is just a number. So you have infinity, something going to infinity, a huge number divided by something. This is still going to infinity. This would be infinity, which is a form of DNE. Okay? If you know which infinity it's going to, back here we didn't know if it was going to positive or negative infinity. But if you know which infinity it's going to, you can say it's equal to infinity, but it is still a DNE. Let's take x to infinity, and this time we have 1,000 divided by, and our x is down here. So this bottom, the bottom is going to infinity. If I take 1,000 and I divide by a huge unbounded number, this whole thing will be going to 0. If you take any number, I don't care what it is, if you take a number, even a large number like 1,000, and you divide by a very large number, you're going to get something tiny. 1 times 10 to the negative 14. That means a 0.0000, 0.00, 14 zeros and then a 1. That's a very tiny number. Okay? Alrighty. So when you plug in your x value, when you're doing substitution, which is always the first thing we do when you're doing substitution, when you plug in your x value, you might just get a plain number, and if you do, great, you're done. I will tell you though that doesn't happen very often. Usually we get something funky going on. Okay, if you get a non-zero real number divided by 0, then your limit is infinity or negative infinity. Okay? Infinity or negative infinity. Okay? If you have 0 on top and a non-zero real number on the bottom, then your limit is 0. If you have a non-zero real number divided by infinity, then your limit is 0. So if infinity is on the bottom, your limit is 0. If infinity is on top, your limit is infinity. Okay? If 0 is on the bottom, your limit is infinity or negative infinity. If 0 is on top, your limit is 0. All right, let's take a look at what's coming up here. Now, that's all fine and good, but the more interesting limits are when we get an indeterminate form, when we plug in that x value. There are several indeterminate forms. What happens if you get 0 over 0? Infinity over infinity, negative infinity over infinity. Those are the most common ones we're going to see right now, but there are more, okay? There are more indeterminate forms. Right now, we're just going to take a look at those three. So if you plug in your x value and you get one of these forms, we must use a technique that will allow us to manipulate the function so that we can plug in the x value and get a real number that is not indeterminate. If you have a rational expression and you get the form 0 over 0, this means you have a hole in the graph at that value of x. And the goal will be to manipulate the function so that you can reduce out, cancel out, the factor that contains the hole. So the next method, the next technique is factor and reduce. So the first technique was substitution, and the second one is factor and reduce. You must have good, strong factoring skills for calculus. So if we put in negative 2 for x, I'm going to have a 4 plus 8 minus 12, which is 0 on top, and on the bottom I'm going to have a 4 minus 4, so I get 0 on the bottom. 0 over 0 is indeterminate. You do not have to write this, but for the sake of your notes right now, that is indeterminate. Do not write equals here, okay? A limit is never equal to 0 over 0. Okay? You will not get full credit if you write an equal to sign right there. Okay? All right, so what we do is we're going to go and factor. So since we tried to plug in, but we weren't successful, we have to manipulate. We have to keep writing this limit. So you must keep writing limit every time until you can plug in this x value and get a real number, get an answer. Okay? So I'm going to factor the numerator. The numerator will factor to an x and an x, a 6 and a 2, and the 6 needs to be a minus, so like that. And the denominator is a difference of squares, so this would be x plus 2, x minus 2. And I have found my hole. My hole is when x is negative 2. So x plus 2 are the two same factors, which is when x is negative 2. I'm going to cancel those out, which I can do because I'm only approaching negative 2. I'm not equal to negative 2. So cancel those out. Normally you could not cancel those out. You leave them. But a limit is not exactly equal to negative 2, it's just approaching, so we can cancel those out. And when we cancel those out, we can put this negative 2 into what remains. So I'm going to put my negative 2 in for that x, and in for that x. I know I'm going to get an answer because I have gotten rid of my hole. So we're going to have a negative 8 on top. We're going to have a negative 4 on the bottom. So this limit is 2. Let's go on to B. This time we're approaching 3. So I'm going to put 3 in for x. 3 squared is 9. 9 minus 9 is 0. 3 squared is 9 plus 3. That's 12. Minus 12 is 0. We get 0 over 0, which is indeterminate. So we see if we can factor. So when I see something like this in a limit, I'm thinking, let's just go ahead and factor. The numerator is a difference of squares, so x plus 3, x minus 3. The denominator factors at x and x, and two numbers that multiply to get a negative 12, add to get a positive 1, so that would be a positive 4 and a negative 3. And sure enough, not surprising because we did have a 0 over 0, there is our whole. I knew it was going to be there when I saw the 0 over 0. So we're going to cancel those out, put 3 into the remaining x's, and we get 6 over 7, and that is our answer. Alrighty, part C here. We're going to put 2 in for x. 2 times 4 is 8. 8 minus 8 is 0. Put 2 in down here. 4 minus 4 is 0. That is also indeterminate. I'm going to stop writing indeterminate, but that is indeterminate. So we keep writing our limit. This is equal to the limit as x approaches 2 of time to factor 2x and x. Okay, we might have to play with this a little bit because we have this 2 out in front, but either a 2 and a 3 or a 6 and a 1, right? So I think we're going to need a 3 and a 2 because I want to subtract to get a 1 here. This one needs to be a minus, this one needs to be a plus. Again, you have to have really good, strong factoring skills for calculus. In the denominator, there's a 2 in common, so we're going to take out a 2, like that. And sure enough, not surprisingly, I see my whole. I knew it was going to be there because I got 0 over 0. I knew it was going to be there, I just had to find it. Okay? So cancel those out, put 2 in for the remaining x's, and we get 4 plus 3 divided by 2. And that's my limit. Okay? Alright, D. If we just put negative 3 in for x, negative 3 cubed is negative 27, plus 27 is 0, negative 3 plus 3 is 0. That's indeterminate. So we're going to see if we can factor, right? Find our whole. I know there's a whole, we just have to go find it. So limit as x goes to negative 3. Okay, how do you factor a sum of cubes? How do we factor a sum of cubes? And in class we would talk about that, but you can't answer me, so I'm going to answer for you. So we factor a sum of cubes into a binomial times a trinomial. And the binomial will be the cube root of this, just an x, and the cube root of the 27, that's a 3, and you keep the same sign, right? Then for the trinomial, now I'm just taking a look at this piece. I square the x and write it here. I square the 3 and I put it in the back. For my middle term, I just multiply these together. Ignore the sign, multiply those together. For the signs, same sign, opposite sign, always positive. That's your little soap. Same sign, opposite sign, always positive. Okay? And again, square your x, square your 3. This middle term is the product, ignoring the sign, it's the product. And in the bottom, we cannot factor that, it's just an x plus 3. There's our whole. It has to be there. It has to. Now we're going to plug in a negative 3 into what remains. Negative 3 squared is 9. Negative 3 times negative 3 is 9. And then there's this 9 in the back. So this is 27. That limit is 27. If we graphed that, we would see that. It's going to 27. All right, couple more. Plug in 2 for x. 4 minus 4 is 0. 8 minus 8 is 0. That's indeterminate. We're going to factor. I'm going to rewrite my limit. Up on top, we just have a difference of squares. So that is x plus 2, x minus 2. On the bottom, we have a difference of cubes. So we use our SOAP thing again. It's a binomial times a trinomial. The cube root, same sign, same sign. Okay? The square of your x, the square of your 2, the middle will be the product of the 2 and the x. That was a minus. You want the opposite sign and then always positive. Where's our whole? Our whole is right there when x is 2. So we're going to cancel those out, put 2 in for all of our remaining x's, and we're going to get 4 divided by 4 plus 4 plus 4. So this limit is a third. Okay, one more. X is going to 0 here. X is going to 0. On top we just have an x, so that's 0. And then on the bottom we're going to have 0 plus 0, that's 0. Lots of zeros going on. So that means we have a whole. Let's go find it. On top we just have an x. Can't do anything with x. On the bottom we can factor out an x because there's an x in common, right? We're going to have left an x squared from this term and a 2, a positive 2 from that term. And we found the whole. There's our whole. Cancel it out. Plug in 0 for the remaining x. Everything in the numerator canceled, so it leaves a 1 up there, right? So this is just 1 over 2, 1/2. And again, remember, do not write that a limit is equal to. In all of these, I did not write equal to. If you accidentally do put an equal to sign, scribble it out or erase it. Don't leave it. You won't get full credit if you have an equal to. You cannot equal a 0 over 0. You cannot equal an indeterminate form. Okay, we are going to stop there, and we'll do our next technique that is on the same notes page. We'll do our next technique tomorrow.